Hello, I am Prabhat Sharma, a Senior Solutions Architect at Amazon Web Services. Today we will be covering on how Asana serves millions of customers using Amazon EKS with my partner, Eldar Bogdanov. We'll be covering a short introduction to Amazon EKS, a little bit about the EKS ecosystem, and then Asana's journey to Kubernetes and Amazon EKS. So what is Amazon EKS? It is Kubernetes. It is the open source version of Kubernetes that we provide to you with all its benefits. No extra modifications, no proprietary stuff. It is upstream Kubernetes. Whatever modifications that we make to make it work better in Amazon ecosystem, on AWS, we put that back to open source Kubernetes by working with the community. We make all the modifications to provide you a best experience on AWS, improve and build integrations with other AWS services, and work with the community. Let's talk about the service integrations. We have a lot of service integrations of Amazon EKS, right from CloudWatch, auto scaling, VPC, subnets, X-Ray, and a lot more. We have designed EKS to run production workloads, okay, with large clusters, not 2 nodes, not 20 nodes, but hundreds of nodes. There are customers who are running thousands of nodes on Amazon EKS. Some of the tenets of Amazon EKS are: EKS is a platform for enterprises to run production-grade workloads. It aims to provide features and management capabilities to allow enterprises to run real workloads at real scale. Reliability, visibility, scalability, and ease of management are our priorities. EKS provides a native and upstream Kubernetes experience. Any modifications or improvements that we make in our service must be transparent to the Kubernetes end user. This means that your existing Kubernetes experience and know-how applies directly to EKS. Your existing applications and investments in Kubernetes work right out of the box with EKS. And this is exactly why thousands of customers have chosen EKS to run their applications on. Customers like Fidelity, Snap, HSBC, GoDaddy, Delivery Hero, and Amazon. They run hundreds of workloads running millions of transactions per second on AWS. As an example, Snap uses EKS to run over 2 million transactions per second. Through EKS and ECR, Snap has realized a 77% reduction in developer effort for launching new microservices. 77%. That's a huge number. Let's talk a little bit about Amazon ecosystem for EKS. We provide services like Amazon ECR, autoscaling, and managed node groups, along with AWS App Mesh and Code Pipeline, along many others, to help you run your applications on Amazon EKS. Additionally, we also have a lot of partners providing their products and services on AWS Partner Network that can help you run your applications on AWS securely and at scale, should you need any help. When it comes to compute, Amazon EKS can leverage x86 CPUs and GPUs, along with its serverless counterpart AWS Fargate. It also allows you to run your applications on Spot instances and ARM-based Graviton 2 instances, allowing you to have high performance at a lower cost for your applications. EKS can also be run in your own premises using AWS Outposts, EKS Distro, and EKS Anywhere, bringing you the power of EKS just about anywhere you run your applications. When it comes to observability, how your applications are running. You have tools like Amazon CloudWatch, X-Ray, and Grafana and Prometheus that you can use together with OpenTelemetry. And on top of this, you have a lot of tools and services available from AWS partner networks that you can utilize. When it comes to security and compliance, EKS is highly secure and meets and exceeds a number of regulatory standards like SOC, PCI, HIPAA, FedRAMP, and many, many more. And now we will go ahead and cover Asana's journey to Amazon EKS. I'll hand it over to my partner, Eldar.
Thank you for the introduction, Prabhat. Hi, everyone. My name is Eldar, and I am a software engineer at Asana. Today, I'd like to talk to you about Asana's infrastructure, and specifically how we utilize EKS to run most of our services. So first of all, let's start with what is Asana. We're a work management platform that helps teams organize and execute their work, ranging from daily tasks all the way to high-level strategic initiatives. We have over 89,000 paying customers and millions of free teams in 190 countries across the world. We provide clarity into who is doing what, by when, and serve as a single place for coordination that would otherwise be spread across emails, chats, spreadsheets, and other tools. Let's see what infrastructure powers Asana behind the scenes. We are running about 50 different types of medium to large, internal, and public-facing services. Historically, these services were running on a large number of EC2 machines. Over time, most of them were containerized and managed using Kubernetes. Initially, we used to host Kubernetes control planes ourselves, but later switched to using Amazon EKS for this. Let me share some statistics to give you an idea of the scale at which we utilize EKS. We have a total of about 80 plus clusters running in production, and this rather large number is an artifact of how we use them. Namely, every instance of every service is deployed with its own EKS control plane. I'll talk about the trade-offs of this decision a bit later. Our largest cluster runs over 3,500 Kubernetes pods. In fact, our second largest cluster also has about 3,000 pods, and then the services tend to get progressively smaller. In total, we run about 15,000 pods on all clusters at any given point of time. Finally, we create and tear down EKS clusters very frequently. CloudTrail showed 679 create cluster operations in the months when I was preparing this presentation. We will see where such frequency comes from later on as well. Let me also share a brief timeline of how we got from an exclusively EC2-based setup to EKS first model. In early 2016, all of Asana's services were deployed as a monolithic application and suffered from all of the traditional drawbacks of such architecture. For example, the deployment of unrelated services was coupled together, and one service might be blocked or even have to be rolled back because of the other. We also had a tangled web of dependencies, which were a superset of dependencies needed for each service. Finally, the release team had a very painful on-call experience. When we were developing a new service in 2016, the infrastructure team decided to take a novel approach and containerize the application. They decided to use Kubernetes to handle container orchestration, and remember that Kubernetes was a relatively young project at the time. So to make the job of managing Kubernetes and AWS resources easier, the team built a framework called KubeApps. In mid-2016, we deployed our first KubeApp. KubeApps alleviated a lot of issues at the time, but this is not to say that the framework did not add a bit of its own. For one, Kubernetes is not a particularly simple system to install and configure. So managing a self-hosted solution was adding its own maintenance overhead. That's why when Amazon announced Elastic Kubernetes Service, we were pretty excited to try it out. The first KubeApp based on EKS was productionized in October 2018, and after it proved a success, we have migrated all of our self-managed Kubernetes apps to EKS by July 2020. Let us spend a bit of time looking into what this in-house framework called KubeApps actually is. I think a good way to reason about this is by comparing kubeapps with the features of vanilla Kubernetes back in 2016. So at the time, Kubernetes did not really handle configuration of your resources beyond Kubernetes-specific things like deployments, daemon sets, services, etc. With kubeapps, we wanted to capture all of the configuration of a service in a single place. For Kubernetes resource YAMLs, we introduced a dynamic spec language that lets you generate the YAMLs from Python code. And this feature became really useful when we needed to dynamically change resource definitions based on environment and other things. Kubeapps also provide Python hooks to define what autoscaling groups, ELBs, security groups, and other AWS resources need to exist for your service, while Kubernetes at the time expected AWS resources to be in place when it deployed the app. Although I do believe that Kubernetes added a lot of functionality around this in more recent years. Another point is that Kubernetes does not dabble in how the container images are created. It expects them to be already present when Kubernetes schedules containers. Kubeapps, on the other hand, let you define which images should be built as part of your service and make sure that you are using the image version corresponding to the commit currently being deployed. And finally, kubeapps come with some auxiliary goodies. For example, they update the Route 53 DNS names on your behalf. They also deploy a Chaos Monkey instance along with your service, and they deploy telemetry collection tools as well. So I mentioned before how every service is deployed on its own EKS control plane. There are some trade-offs behind this decision. Let's look at the benefits first. In our model, if a cluster goes down, it only affects a single service deployed on this cluster. By comparison, if we had all of our services running on a single cluster that failed, we would lose all of them at once. Moreover, isolating services from each other this way eliminates the possibility of their resources interacting with each other on Kubernetes level. For example, if your RBAC permissions are misconfigured. Neither can different services cannibalize on each other by taking up too much of the underlying node capacity. Isolation also provides some security benefits because different services specify their own IAM roles and security groups. Imagine a scenario where you want to share a node between services that have different permissions. In that case, you need to give a superset of all of these permissions to the node. So here I want to mention that EKS actually provides an awesome feature of giving each pod its own IAM role, and I believe security groups as well. But we haven't utilized this yet in our setup. There are some downsides to running each service on its own cluster. First of all, there are infrastructure costs. We are not only paying for the extra EKS control planes, which are actually relatively cheap at about $900 a year, we are also paying for underutilized node capacity. Like for example, we deploy telemetry collection tools and Chaos Monkey in every cluster, and we need extra capacity to support them. In a shared cluster, we could just share these tools. Moreover, because even small services have to define the AWS resources needed for the application, like autoscaling groups, for example, they need to actively reason about the capacity required for their workflows. Those prepackaged telemetry collectors and Chaos Monkey pods, they complicate the reasoning around available node capacity. Let's talk about the deployment patterns in kubeapps. That is how the code gets updated. So on this slide, we can see a kubeapp during its normal operation. There is an EKS control plane. There are autoscaling groups. There are Kubernetes resources deployed on the nodes, an AWS load balancer in front of this infrastructure, and a DNS record that points to the load balancer. The first type of deployment is a full update. The idea here is that we create a full new cluster, including the control plane and all of the resources on it, but the DNS continues pointing to the load balancer of the old cluster, which continues serving traffic while the second cluster is being spawned. Once the new cluster is ready and passes all the health checks, we switch DNS over to its load balancer. As a result, the new cluster starts serving traffic, and we could keep the old cluster on standby for some amount of time. Let's say your team found a bug in the new release and needs to roll the changes back. As long as your old cluster is still around, a rollback can be achieved by simply pointing DNS to the load balancer of the old cluster. So this idea of immutable infrastructure gives us some nice benefits. For one, operation of the service is never affected during the deployment, no matter how broken the new version of the code might be. We can also guarantee that the deployments don't depend on the state of the cluster, and the service can be created from scratch. That's what we're essentially doing with a full update every single time. And I guess the ability of rolling back, like we've shown previously, is also an artifact of immutable infrastructure. There is a single downside to all of this. Namely, creating a new control plane and new AWS resources takes a considerable amount of time. So full updates are relatively slow. EKS itself seems to take around 13 minutes to start, at least with the CloudFormation template in our case, and the subsequent AWS resource creation takes at least a couple minutes more, sometimes up to 15 for our very large clusters. The second type of updates in KubeApps is a rolling update. It works pretty much the same way a normal Kubernetes rolling update works, which is it gradually shuffles the pods for new ones. So during the update, you are running a mix of old and new code on different pods. And this makes it sometimes hard to reason about the intermediate state of your service when you have half the pods running new code and the other half running old code. Know that rolling back such an update essentially means performing a rolling update to the previous version of code. So they cannot be as fast as the full update, which just switched the DNS over. There is one thing we get back though when we use a rolling update. It is the speed of a normal deployment. Because we don't have to create all of the underlying AWS infrastructure from scratch, the only overhead is to shuffle the pods, assuming the images have been pre-built. At Asana, a common model is to perform a full update of a service on a weekly basis, and then do rolling updates on every other day, or maybe even multiple times a day. So you might be interested in how these various services deployed as KubeApps and in EC2 instances communicate with each other. We used an approach commonly known as service mesh. In a nutshell, the idea is that instead of each service trying to figure out how to talk to downstream dependencies, we abstract this task away to a single component, which can be added to any service. The component maintains the table of all services, their DNS, and the intended protocol of communication. At Asana, service mesh is implemented using Envoy. More specifically, we have a sidecar Envoy container running adjacent to the main application in each pod that needs to talk to external services. And whenever the main container wants to communicate externally, it makes a request to a specific port on localhost, which Envoy listens to and routes the request accordingly. Similarly, we run Envoy on our legacy EC2 instances to allow them to communicate with KubeApps. Let's explore a bit deeper the reasons why we moved to EKS. I previously mentioned maintenance overhead incurred by managing our own Kubernetes. Probably our biggest pain point was that prior to EKS, our largest clusters sometimes came up with broken networks, and we weren't always able to diagnose the reason, although we were suspecting that it was related to our self-managed Kubernetes setup. Switching these clusters to EKS alleviated the problem. With EKS, we also get a much better trail of what's going on in the system through the combination of CloudFormation events, CloudTrail, and EKS control plane logs. EKS provides worker node machine images that have up-to-date packages and security practices. Before EKS, the work of updating our worker node setup would fall on our shoulders, or more likely be overlooked. Another nice feature of EKS that we plan to utilize is pod-level IAM roles, and we talked about it previously as well. And last but not least, by using EKS, instead of hosting Kubernetes ourselves, we get the ability to ask for help from AWS support on Kubernetes-related issues, which is really useful because AWS has deep domain experts in this field. So we do face some challenges with our EKS setup, and let me mention a couple here. First of all, EKS actively maintains 4 to 5 minor Kubernetes versions at any given moment, and this continues support after about a year. This means that teams need to continuously upgrade their infrastructure to match the newer Kubernetes changes. On one hand, it's obviously a good thing, as we get access to improved security and newer Kubernetes features. This is also in line with pretty much any software out there. They all reach their end of life at some point. Still, the effort of reviewing the changelogs and updating our Kubernetes definitions across multiple services on a quarterly basis is not negligible. Another somewhat unexpected issue was born from the combination of our networking setup, our decision to run an EKS cluster per service, and AWS's hard limit of 50 tags per resource on all resources, including VPC subnets. When you deploy an EKS control plane, it adds a tag to every subnet it has been deployed in. Our networking setup includes a single giant subnet in each availability zone, which might already have some tags of its own for unrelated purposes. So for high availability, we need to deploy EKS control plane into more than one availability zone. And originally, we were deploying the control plane into every single availability zone that we had. So as a result, we eventually ran into this 50 tag per resource limit. For now, as a workaround, we have reduced the number of availability zones that we deploy the control plane into, but as the number of clusters grows, we'll have to think of a different solution. So what's ahead for EKS at Asana? One feature that we have been eyeing is Fargate. Remember those autoscaling group definitions that KubeApps need to specify? We want to remove the overhead of thinking about resource utilization from service owners, and just let them specify the Kubernetes resources that they need and nothing else. Fargate is a way to let AWS handle node allocation and remove this responsibility from each individual service owner. Moreover, our EKS setup has proven reliable in the many months we've been running services on it, so we feel confident in moving the rest of legacy EC2-based services over to Kubernetes. We see great benefits in consolidating our infrastructure and see EKS as the primary way to run our services going forward. That's all I wanted to talk to you about today, and thank you for listening.